Welcome everyone. This is Gokarna Sharma from Kent State University. I will talk about our paper, Weak Amnesiac Plotting of Multiple Messages. Plotting is a fundamental problem in distributed systems. Here, our message theta is given on a source node of graph Z. The goal is to disseminate theta to all the nodes of Z. So we want to provide some guarantees. For example, there is a correctness guarantee that all graph nodes should receive message theta. And then there has to be termination that message theta should not be in transit after all the nodes receive theta. So at some point in time, there has to be no message in transit. So in classic plotting, this termination guarantee is achieved using storage record. So basically, nodes keep record of whether the message theta is seen before or not. If it is seen before, then they will discard it and do not forward it. So that guarantees that there is a termination and messages do not stay in transit for a long time. So actually in synchronous message passing model where computation proceeds in rounds, then termination is guaranteed in d+1 rounds where d is the diameter of the graph. So recently, Wouzak and Trehan considered amnesiac plotting. So basically here what happens is that what if nodes have no record of whether theta is seen before or not? Then there is a challenge, right? Because the message might travel all the time and then the message is in transit and termination may not be guaranteed. But surprisingly, what they proved is that there is a termination even without having message record. So and the termination is E rounds in bipartite graphs and between E and E plus D plus 1 rounds in non-bipartite graphs, where E is the eccentricity of the source node. And per the asynchronous model, it is impossible to achieve termination. So recently, they extended the amnesiac plotting model to dynamic amnesiac plotting, where you have multiple messages. They might start in multiple rounds and from possibly multiple source nodes. And then the goal is again to achieve correctness and termination per each of the messages. So they consider three variations: partial send, ranked full send, and unranked full send. So for partial send, a node only sends a message to its neighbors from which it did not receive any message in the previous round. Ranked full send, a node will send some highest ranked message to all neighbors from which it did not receive that message in the previous round. So for these ranked ones, so messages are ranked, and then you have the nodes, they need to know the rank so that they can always send the highest ranked message. So in unranked, it's similar to ranked full send, but the message rank is not known. So Wouzak and Trehan, they showed that the first case terminates, the second case also terminates, but third case it does not terminate. So what we saw in this paper is that the third case, unranked full send, also terminates if graph nodes know diameter of the graph. And then the termination time is 2k minus 1 times d plus 1 in bipartite graphs and 2k minus 1 times 2d plus 1 in non-bipartite graphs, where k is the number of messages. What is the technique? So we calculate wait time based on local rank. So they do not need to global rank because they don't know the global rank, but local rank they will know. And they will update the wait time if local rank increases during the algorithm. And then, so the messages will be plotted. The lowest ranked message will be plotted in each round following the algorithm of Wouzak and Trehan, the single source algorithm. And then running that algorithm, what we saw is that for globally k prime ranked message, without knowing rank, the local wait time update stops at k prime minus 1 times 2d plus 1. And if globally k prime ranked message starts plotting at round k prime minus 1 times 2d plus 1, then it finishes plotting by round k prime 2d plus 1. So basically what we guarantee is that for k prime ranked message, it will finish plotting by k prime times 2d plus 1. And then that guarantee gives us the solution. Okay. So why our approach is weak amnesiac? So since nodes know D, they need to know log bits at each node to keep track of D. So they have to store that information. And we have wait time that needs log k plus log bits because it depends on K and D. So therefore, the total memory requirement for our algorithm is log max k comma d bits per node. And then when we compare to classic flooding, for k messages, classic flooding needs at least k bits per node to keep track of these messages, and amnesiac flooding, no record. So we are somehow weaker than amnesiac flooding, stronger than classic flooding, because we reduce the memory requirement significantly. And similar to, and then compared to dynamic amnesiac flooding variations studied, we reduce the time. So in future, whether without knowing D or maybe knowing weaker parameter than D to achieve this kind of result is left for open future work. Thank you for listening to this short talk. And then if you have any questions, please reach out to me at my last name at cs.kent.edu. Thank you very much for attending this talk. Thank you.